I would like to design a circuit for adding numbers in binary. Let's start with just single bit addition. Single bit, obviously, I'm just adding one bit. Let's look at every possible combination, right? If I'm adding 0 plus 0, my sum is a 0. 0 plus 1, the sum is 1. 1 plus 0, that's really the same thing. I also get a 1 as a sum. 1 plus 1 is a 2 in binary, or you could think of it as 0, carry a 1 out to the next column. This is a 2 in binary. So if I fill in the truth table, 0 plus 0 is 0, 0 plus 1 is 1, 1, 0. Here's my 1 plus 1 is 0, carry out a 1. So this C out is my carry out column, right? And if I add 0 plus 0, 0 plus 1, there's no carry out in any of these cases, except the very last case, I get a carry out. So here I have the equations for the sum column and for the carry out column. And you can see that the sum column, I have a not A and B, and I have an A and a not B. And here are my two terms, right? Here you've done this a million times. You know how to write these Boolean expressions. And my carry out column is even easier. The only place I have a 1 is when I have an A and B. That's why my carry out equation is just A and B. And you've done this many, many times. So remember, the goal of this is to come up with a circuit for adding numbers in binary, and I can draw my circuit for the sum. That's pretty easy. So here's my input switches A and B. First, I need a not A, that's a not, ANDed with a B, and then I need an A ANDed with a not B. I know my AND gates are a little messy there. Sorry about that. That is my not B going into my and I'm going to OR the result. Well, that's not too bad. That is my sum of my single bit addition A plus B is my sum. Wait a minute. I think I could do better than that. Isn't this sum column just an exclusive OR, right? I mean, perhaps you recognize this as an exclusive OR, right? It's either A or B, but not both. So I think I can redraw my sum a little bit easier than that. I can draw it as just A exclusive OR. Remember how to do an exclusive OR? It's got like two little lines in the back. Exclusive OR. Wow, that's kind of a mess. Exclusive OR with B. That's it. And the symbol for exclusive OR, and maybe you have not seen the Boolean symbol for this yet, is a plus with a circle around it. So it's like an OR with an extra circle. So remember this, you can add, this is just my sum column. You can add two bits, A and B, just by using an exclusive OR. And isn't that easier than the ands and ORs and nots? That's it. Let's draw the full circuit now for the sum and the carry out column. Now already you know that the sum is just going to be an exclusive OR, so I'm exclusive ORing A and B. This output is my sum, and the AND gate is, of course, the carry out. Remember, a carry out is just when I have a 1 in the A and B column. So I'm just going to use an AND gate for this. When I have A and B, I get a carry out, and I'm just going to run the inputs to A and to B. Try not to be too messy. And that is my carry out. That's the circuit. Now let's take a look at multiple bit addition. How do you add more than just one bit? Well, let's start at the beginning. So I have a 1 plus 0, which you know, of course, is a 1. 1 plus 1 is 2 in binary, or you could think of it as a 0 carry out a 1. So I've carried out a 1 to this column. Now in this column, you could think of it as a carry in, right? I'm carrying into this column, and I've carried out from the previous column. So I have a 1 plus 1 plus 0, which is a 2 in binary. So I'm going to, again, a 2 is a 0. I'm carrying out a 1 into this column. Well, in this column, I'm calling it a carry in. And I hope that makes sense, right? From this column, I'm carrying out. Into this column, I'm calling it a carry in. I've carried in a 1. So I have a 1 plus 0 plus 1, again, is a 2 in binary. 0 carry out a 1. So now I've carried in a 1 to this column. I have a 1 plus 1 plus 1, which is 3. In binary, a 3 is a 1 carry out a 1. So there I have added my multiple bit binary number. Now let's fill in the truth table for one of the columns in my multiple bit addition problem. So I'm adding a plus b plus a carry in. Of course, if they're all zeros, I get a 0, no carry out. I have 1 as an input, so my sum is a 1, no carry out. Again, sum is a 1, no carry out. 1 plus 1 is 2, so that's 0, carry out a 1, 1, 0. I hope I'm not going too fast. 1 plus 1 is 2, which is a 0, carry out a 1. 1 plus 1 again is 2, which is a 0, carry out a 1. And finally, my last column, 1 plus 1 plus 1 is 3, which is a 1, carry out a 1, right? A 3 in binary is 1, 1. So let's complete the equations for my output columns. The sum, and I think if you give this some thought, you will agree, it's really just the exclusive ORing of all of my inputs. I'm going to exclusive OR A with B, exclusive ORed with my carry in column. Exclusive ORing really gives you a 1 if you have an odd number of 1s as inputs. So here I have an odd number of 1s as input, right? Just 1, 1. Here again, I have an odd number of 1s as inputs. Here I have an odd number of 1s. And finally, here I have an odd number of 1s, right? That's really what exclusive ORing does, if you have one or the other, but not both. Right, so this hopefully I think should make sense. Exclusive ORing A, exclusive ORed with B, exclusive ORed with carry in. That's my sum. My carry out column, even easier to think about. You get a carry out if you have at least 2 1s as inputs. So my carry out, in this first case, I have B and carry in, all right, ANDed together. So my carry out is B and carry in, or what's my next one there? That looks like A ANDed with carry in, A ANDed with carry in, and then I have A ANDed with B, that's A and B, and this last one, I guess I could write A ANDed with B ANDed with carry in, but you would see that if you tried to simplify this with Boolean algebra, you could actually get rid of this last term, right? It's really, I get a carry out if I have any 2 of these inputs ANDed together. B and C, or carry in, A and carry in, A or A and B. That is my carry out. All right, let's take a look at the circuit. So this is what the circuit looks like for adding 2 numbers, I should say, 2 bits in a multiple bit addition problem. My sum is just the exclusive ORing. We looked at this already. It's the exclusive ORing of A, exclusive ORed with B, exclusive ORed with the carry in. And my carry out is, of course, A ANDed with A ANDed with carry in, or it looks like B ANDed with carry in, or it's just every possibility of my inputs, or which one am I missing? Or A ANDed with B, right? It's either this and this, or this and this, or this and this. That's it. That is my carry out. So the good news is that if you actually want to add 2 bits in a multiple bit addition problem, you do not have to make the circuit using all of these discrete gates. This would be called small scale integration, SSI, using a small scale integrated circuit chip. You can actually use a chip, a 74183 chip, which actually has all of that logic built into it. And you remember, if a chip has more than 10 logic gates on it, it's called a medium scale integrated circuit. So you can use this chip, the 74183, if you want to build your full adder circuit. Here is a diagram of a circuit that you would build to add a 4-bit binary number, or I should say two 4-bit binary numbers, right? So like if I want to add 1100 and 10, I don't know, 10. Of course, for the ones place, 0 plus 0 is just 0. You don't really have to worry about a carry in. That's why over here on the bottom, this is my least significant bit. This is the ones place. Notice how this circuit right here at the bottom, there is no carry in. All I have to worry about is a carry out from this guy into the next circuit. So here I have the carry out going into this AND gate, into this AND gate, and into the exclusive OR, right? So this is a carry out going into the next circuit. Now here it would be called a carry in. So this is my least significant bit representing the ones place. I shouldn't write a 1 there, that's going to be confusing. This is my ones place, this is my twos place, my fours place, my eights place, also called the most significant bit. And this is my least significant bit. So here is my carry out, and let's see. So from the next circuit, my carry out, of course, goes up into the next most significant bit. And then here's the sum of that. And then I have another carry out going up into the next circuit for my most significant bit. So here I've chained together. And again, this first adder is sometimes referred to as a half adder because you don't have to worry about a carry in. You just have to worry about a carry out. The rest of the adders are called full adders. Full adders have to be able to deal with a carry out to the next place, as well as a carry in into that circuit. So in this last slide, we have a picture of the simplified. I've used the adder chips, right? Do you recall a couple of slides ago I showed a diagram of the 74183 chip. This is a medium scale integrated chip, and this is much simpler to understand what's going on. This is my ones place, or the least significant bit. And well, here I have a carry in, but I've tied it to ground. So really there is no carry in. This is a 0. And of course, this carry out goes into the next carry in. This carry out goes into the next carry in. And this carry out goes into the next carry in. So this is my ones place, my twos place, my fours place, the eights place, or the most significant bit. And that's it.